Where do all the elements come from? Where do hydrogen, helium, up through uranium come from? Where were they made? Are they still being made to this day? And how well are we confident in our ideas about where these elements came from? These are the questions we're going to be taking up in this lecture we entitle, We Are Made of Star Stuff, The Origin of the Elements. My quote about star stuff is taken from a quote from Carl Sagan from his 1980 television series Cosmos in Episode 9, The Lives of Stars. It reads, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff." Sagan answered this question in his very influential series Cosmos. Many scientists from my generation today still say how they were deeply influenced by Sagan's groundbreaking series. I have to confess I'm not one of them. But the reason is, well, I didn't see it. In 1980, in the fall, I was a sophomore at Caltech majoring in physics, and, well, my course load was pretty crushing. I also didn't live in a place with a TV. Second confession, I didn't live in a house with a TV between the time I left for college and about the time I became a full professor. Just kind of the way it is. So as a consequence, I missed the entire series. I've actually seen one episode. It was the episode entitled Who Shall Speak for Earth. Every now and then, PBS would re-air the original Cosmos series, and I'd see it up on TV, and I'd catch an episode. And for whatever reason, I always caught the same episode. I did this 3 times, and, well, I didn't really finish it the 3rd time because I'd already seen it. I also didn't get to see the 2014 reboot of the Cosmos series by Neil deGrasse Tyson. The reason was also I was kind of busy and away from a television. It was a time when I was working on a new spectrograph for the Large Monocular Telescope and kind of occupied. Maybe one of these days it'll come up in my Netflix queue, but until then, we're kind of left with this quote. So let's get back to our main question. Where does all of this stuff come from? Where does hydrogen, helium, the lightest elements, all of these other elements we call the metals, all the way up through uranium and beyond? Where does it come from? We have to explain this with a compelling scientific answer. And a compelling scientific answer for the origin of all the elements must explain in detail not only the origin of these elements, but correctly explain their relative abundances. This is a somewhat complicated plot that spans 15 powers of 10. It shows all of the elements arranged by their atomic number, which is the number of protons inside their nuclei. It begins with the 2 most abundant elements, hydrogen and helium, and then shows a particular pattern. Notice this pattern is zigzagging up and down. There's a reason for that zigzag pattern, extending all the way to uranium. And this zigzag pattern has to do with the mix of the number of protons and neutrons inside of the nuclei. Where does this patterning come from? It isn't enough to say, well, all of the elements heavier than hydrogen and helium came from stars. That's an easy answer. The hard answer is, why is there this zigzag pattern? Why is it some elements are more abundant than others with a very systematic pattern? Why is there a big peak here at iron? Things like lead and bismuth and thorium and uranium are among the rarest elements in the universe. Let's begin our story. Hydrogen, the simplest of the elements, 1 proton, today is mostly surrounded by 1 electron, was made during the Big Bang when the universe was only about 1 microsecond old. At this time of the universe, the temperature of the universe had dropped below 10 to the 13 degrees Kelvin. At this temperature, it had dropped below the binding energy for quarks to bind together into protons and neutrons, and heavier particles known as hadrons. So once the universe had dropped below 10 to the 13 degrees Kelvin, all of the free quarks and gluons that had existed in the expanding fireball of the Big Bang suddenly condensed to form the hadrons, the heavy particles, mostly in the form of protons and neutrons. Other forms of hadrons would have formed, but they are unstable and eventually decay into these most basic of particles. A proton consists of a pair of up quarks and a down quark, and a neutron consists of an up quark and a pair of down quarks. One of these down quarks in the neutron and one of the pair of up quarks in the proton are an antiquark. It was still too hot in this phase for these protons and neutrons, which fill the universe along with all the photons from the cosmic fireball, and electrons and neutrinos couldn't form together into anything heavier. As soon as a proton and a neutron fused into a heavier nucleus of deuterium, the first heavy isotope of hydrogen, it was immediately broken apart by colliding with a high-energy photon. At this phase, the universe was too hot for nucleons, protons and neutrons, to bind together in nuclei. And so matter as we understood it didn't exist. In effect, the universe was pure hydrogen plus neutrons and electrons and photons and neutrinos. But this changed as the universe expanded and cooled. Helium and traces of deuterium and lithium formed between roughly 3 to 15 minutes after the Big Bang during the period we refer to now as the epoch of nucleosynthesis. It became finally cool enough for a proton and a neutron to fuse into a deuterium, a heavy hydrogen nucleus, emitting a gamma-ray photon. This deuterium could then fuse with a second neutron to form a heavier isotope of hydrogen, tritium, with the emission of a gamma-ray photon, and that tritium, colliding with a proton, would be able to form a nucleus of helium, 2 protons plus 2 neutrons. The helium nucleus being lighter than a tritium plus a proton, it also gets rid of its excess mass by emitting a photon. There's an additional channel in which the tritium can collide with helium as helium begins to accumulate in the early universe, forming a stable nucleus of lithium-7 and emitting a photon in the process. But this only occurs towards the end of the epoch of nucleosynthesis. Eventually, the temperature of the universe dropped below a few million degrees Kelvin, and it became too cold for further fusion to begin. At 3 minutes, when the temperature dropped below 1 billion degrees, it was finally cold enough for stable nuclei to form, but the temperature quickly dropped below the point that no further fusion reactions could occur. As a consequence, only hydrogen and helium and traces of deuterium and lithium and a little bit of beryllium and boron came out of the Big Bang. So this only gives us the first 3, 4, 5 elements of the periodic table. Well, where do the rest of the hundreds of elements come from? All of the other elements that we see in the periodic table are made in stars by a process of core nuclear fusion or during extreme transformation events like supernova explosions. In high-mass stars, those stars whose masses are greater than about 8 times the mass of the Sun, those stars at the end of their life will go unstable as core collapse supernovae, ejecting the hydrogen and helium in their envelopes, but also enriching that material with elements made up through iron and nickel. 4 to 8 solar mass stars, what we would call intermediate mass stars, at the end of their lives eject hydrogen, helium, and small amounts of carbon, nitrogen, and oxygen after they reach the end of their asymptotic giant branch, or AGB phase. And finally, low-mass stars, stars with masses less than about 4 times the mass of the Sun, eject their hydrogen and helium envelopes at the end of their asymptotic giant branch phase, leaving behind a core carbon-oxygen white dwarf, and sending out their envelopes with hydrogen and helium that they were born with, plus a very small amount of helium and perhaps a little bit of carbon, nitrogen, and oxygen made during the last phases of the star's life, when the products of nucleosynthesis in the hydrogen and helium shells can be dredged up and make its way into the envelopes. The exact proportions by which these elements make it into the AGB envelopes is one of the things that we're still trying to understand in detail, even if we think we understand it reasonably well in outline. And so if we take now a look at an assay of all of the chemical elements around us, and we ask, what are the top 10 most abundant elements? We find the first and second are hydrogen and helium, followed by oxygen, carbon, neon, nitrogen, silicon, iron, magnesium, and sulfur. These are the top 10 most abundant elements we see not only around us in the solar system, but everywhere else in the universe where we can do a detailed assay of the chemical elements. Of these top 10 elements, only those shown here in blue are the products of supernova explosions: oxygen, carbon, and neon, silicon, iron, magnesium, and sulfur. 2 of the elements, hydrogen and helium, come primarily out of the Big Bang. And nitrogen does not preferentially arise in supernovae, but arises, as we're going to see, in the explosion, the ejection of the envelope of an intermediate mass star at the end of its asymptotic giant branch lifetime. Let's look at the origins of each of the different groups of elements in these different kinds of fusion or transformation events. If we look inside the core of a massive star, a star whose mass on the main sequence exceeds about 8 times the mass of the Sun, at the end of its life, just an instant before the star goes supernova, we will find an inert iron-nickel core, the iron and nickel being the product of silicon fusion, surrounded by a thin silicon fusion shell, which in turn is surrounded by a thin oxygen fusion shell, which in turn is surrounded by a neon, then carbon, then helium, then hydrogen fusion shell, all embedded inside of an immense, cool, extended envelope made primarily of the elements the star was originally born with. On this scale, I haven't shown the envelope to scale because for a star of, say, 15 times the mass of the Sun, which I'm portraying here in this cartoon, the outer envelope would be a red supergiant star, which would extend out to nearly the orbit of Jupiter if placed in our solar system. All of the action occurs in the very center, which is barely bigger than the size of our Earth. The inert iron-nickel core has roughly the radius of the Earth, but it's nearly 1.4 to 1.5 times the mass of our Sun. At the end of the silicon burning day, this core becomes unstable against gravity, and with no other fusion source able to be tapped to hold it up once again, the core collapses and bounces and results in the star exploding as a supernova. The collapsed core continues along its way to become a neutron star, or if a very massive star, it can become a black hole. What we're most interested in is what happens in the explosion, what happens to the envelope, and all of these different layers surrounding that iron-nickel core. It's on its way to becoming a neutron star or black hole. What becomes of the rest of it? What becomes of it is an explosion that forms a lot of heavy elements. Most of the oxygen in the universe is made in high-mass star or core collapse supernovae, like I've just described. During the explosion, there is explosive nucleosynthesis that occurs. The temperatures and the shock waves that go tearing their way out through the envelope are sufficiently high to allow rapid nucleosynthesis, rapid fusion reactions to occur. These further augment the elements that were made in the core. These elements, heavy elements made all the way up to iron and nickel, are blasted out along with the remnants of the envelope of the star, moving out many solar masses of material. The neutron star left behind, when a 15 solar mass star explodes, may only have 1.5 or 2 times the mass of the Sun. The other 13 plus solar masses of material are blasted off in the supernova explosion. This ejected gas, polluted with heavy metals during the brief fiery instance of the explosion, are ejected, expand out into the interstellar medium, and after about 100,000 years, they mix in and combine their metals with all of the other interstellar gas. It's out of these subsequent generations of stars that new elements will be born with these elements. These explosions make most of what we call the alpha elements in the universe. An alpha particle is an old-fashioned name from the late 19th and early 20th century for a helium nucleus. As you may recall from Unit 2, where we talked about the fusion of stars, a lot of the fusion reactions that occur in massive stars are fusion of helium with other elements, or elements made from the fusion of helium. Each of these elements, carbon, oxygen, magnesium, neon, silicon, sulfur, argon, calcium, titanium, and chromium, are made out of these various fusion reactions, all of which involve what we call multiples of the alpha elements, of 2 protons and 2 neutrons. And what we find in the ejecta coming off of these giant core collapse supernovae are primarily the alpha elements, principally oxygen, but also a mixture of all of these other elements. Massive star core collapse supernovae occur probably every 50 to 100 years in the Milky Way. When we look at them in X-rays and in visible light wavelengths and do spectroscopy, we can see that the X-ray spectra, for example, of supernova remnants, like this one shown here, are very rich in silicon, but somewhat less in elements like iron and nickel. Oxygen does not have any convenient emission lines, but when it is seen, it can be seen to be in fairly strong abundance. We also see it in strong abundance when we look at the spectra of supernova remnants using visible and near-infrared spectroscopy. We can see in the remnants blowing off of these explosions a lot more of these elements than they were born with, so much so that the presence of these elements actually dominates the spectra that we see, especially at X-ray wavelengths. As a consequence, what we've learned is that supernova, the core collapse of a massive star, indeed makes a lot of the elements, but it doesn't make a lot of the iron and nickel. It makes a lot of oxygen and carbon and other elements, but not iron and nickel. Where does all the iron and nickel come from? And what about all the other elements in the periodic table that are heavier than iron and nickel? Well, we're going to look at the origin of those elements in the second part of this lecture.